We have a charged particle moving through an external magnetic field. This magnetic field, as you know, is directed into the page. And then that charged particle experiences a force. We can find the direction of that force by using the hand rule for deflection, specifically the left-hand rule for deflection. We stick our left thumb in the direction of the particle, fingers go in the direction of the field, outstretched, right, because it's the hand rule for deflection, and palm points in the direction of the magnetic force. There's a magnetic force acting on that particle downwards, which ultimately is going to cause that particle to be deflected, not downwards per se, but in between to the right and downwards. So it's going to end up going down here somewhere. Ultimately, that's going to cause a force in a different direction, which is going to change its direction, which is going to cause a force in a different direction, and so on. Ultimately, this charged particle is going to end up going in a circle as a result of this magnetic force. This magnetic force causes a centripetal force. What happens if I have another charged particle, another electron, let's say, in an external magnetic field? Got another one right here. It's moving to the right. Well, it experiences a force downward as well. In fact, the exact same thing happens to this one as happens to the first one. It's going to be deflected downwards and ultimately go in a circular path as a result of that. We can analyze the motion of both of these particles, either or both of these particles, by using one of three equations. F is equal to QVB. F is equal to mv squared over r, because it goes in a circle, right? Always goes in a circle. So the centripetal force applies here. And because that centripetal force is caused by the magnetic force, we can also set Fc equal to Fm. But what if these two electrons, what if there's more electrons even than these two electrons? They're moving to the right just as they are right now, but they're not moving through the air. They're not free to do what they want to do. Rather, they're moving through a wire. So we got a conductor here. Maybe it's copper, maybe it's aluminum, doesn't matter what it is. Okay, it's a wire, it's some sort of conductor. These electrons are still moving through this conductor. What do we call that, by the way, when electrons move through a conductor? Yeah, it's electric current. These electrons are moving through the conductor. There's an electric current. They experience a force, just as they did when they were moving through the air. They experience a force. What's the direction of that force? It's exactly the same direction as it is when the particles are moving through the air. The direction of the force on both of these particles is downward toward the bottom of the page. Thumb, fingers, palm points downwards. For the other one, thumb, fingers, palm points downwards. The force is the same, but this time, they're not going to go in a circle like they did before. Why not? Yep. I'm sorry? Yeah, there's a path they have to follow, and that path is the conductor. It's the wire, right? They can't go in a circle. They're kind of held in place. It's kind of like you got a hallway. You're walking down the hallway, and someone's trying to push you going this way, and you want to go in a circle as a result of that force, but you can't because there's a hallway, a narrow hallway that's keeping you going in a straight line. These charged particles go in a straight line instead of going in a circle because they're held in that straight line by the wire. But there is an effect, okay, beyond just the force on the individual electrons. Rather than the electrons going in a circle, okay, the wire itself will experience a force in this case as well. So the force on the particle is QVB. The force on the wire would be ILB. What's I stand for? Sorry, let me ask you that question last. B stands for the magnetic field strength, right? What's L stand for? What is it? The length of the wire. Let's be a little bit more specific with that, though. The length of the wire that is... Good. The length of the wire that is exposed to the magnetic field. Let's be a little bit more specific. The length of the wire that is exposed to the magnetic field and is the current running through it, okay? All right. Looking for the P word. The length of the wire that is exposed to the magnetic field and is perpendicular to the magnetic field, okay? Length of the wire that's exposed to the magnetic field is perpendicular to the field. Good. So the magnetic force is equal to I times L times B. L is the length of the wire. B is the magnetic field strength. What was I? Nathan? Yeah, it's the electric current. And sometimes they're given the value of the electric current in amps or in coulombs per second. Sometimes they're not. Sometimes we're going to find the value of the electric current, and we're going to find that by using the equation on your data sheet, Q over T. Looks like here we got coulombs per second for the units, right? How does a coulomb per second relate to an amp? I'll give you a hint, it's not very hard. Directly, yeah. In fact, it's 1-to-1. It's exactly the same, right? It's identical. 1 coulomb per second is exactly the same thing as an amp. All right, let's take a look at the homework questions we had last night on page 605. Okay, let's have a look at number 2. It says a thin conducting wire 0.75 meters long has a mass of 0.06 kilograms. What's the minimum current required in the wire to make it float in a magnetic field of magnitude 0.15 Tesla? There's a big word here, an important word here. What is that important word? I mean, it's all important, right? But what's the one that kind of jumps out at us that kind of leads us into a certain strategy for solving this problem? Yep, float, right? Float, we've seen that before. Not that specific word before, but something that means the same thing as the word float. Hovers, suspended, remains the same height, goes parallel to the Earth's surface. So when something floats, what are we going to do? What are we always going to do when something floats? Yep. Yeah, some force has got to be equal to gravity. In this case, it's going to be a magnetic force equal to gravity. Now, other times we've done this and set magnetic force equal to gravity, it's been a charged particle that's just moving parallel to the Earth's surface. So QVB would be equal to m times g. This time it's the wire itself that's floating. So what are we going to make equal to m times g in this case? Not QVB, but rather ILB. Good. All right, we're looking for the electric current here that's going to make it float. So we're going to say I is equal to mg over L times B. 0.060 kilograms. Careful on this. The units are kilograms. They're standard units. This is the units we always want to use. But a lot of times you get a question involving something like this. It's going to be in grams. So just be aware of that and be ready to convert if you need to. G is 9.81. Same deal with the distance, the length of the wire. Oftentimes it's going to be in centimeters as opposed to meters like it is here. Magnetic field strength 0.15 Tesla. Do the math on that one. I think we should end up getting 5.2 amps. So tell me what's going to happen. We have 5.2 amps. It's going to float, right? It's going to remain in the same position above the Earth's surface. It's not going to go up. It's not going to go down. What would we have to do to make this go downward, but at a rate less than 9.81? Okay, what would we have to do to this to make it not float, but it's still not falling at 9.81? How would we change this? How would we change the current there? Reduce the current, right? If you make a smaller current, you're still going to have a magnetic force pointing upwards here, but that magnetic force would be smaller than gravity, which would mean that it would still accelerate downward, but at a rate lower than 9.81. What would we do if we wanted to accelerate upwards? Not hover, remain in the same position, but start moving upwards. In fact, start accelerating upwards. What would we have to do to the current then? Increase the current, right? That's going to give you a stronger magnetic force, stronger than the force of gravity, so it accelerates upward. Here's the tough one. What if we wanted to accelerate downward at a rate more than 9.81? What if we wanted to speed up at a rate of 13.7 meters per second squared downwards, or 20 meters per second squared downwards? What would we have to do to the current now? Jeremy? Good. Change the direction of the current. If you change the direction of the current, that's going to change the direction of the magnetic force, which is going to start pointing it downwards, which is going to help gravity as opposed to act against gravity. Right? What's another way we could do that, by the way, besides instead of reversing the current? What's another way that we could cause this thing to accelerate downward at a rate more than 9.81? Yep. Change the location of the wire. I'm not sure what you mean by that exactly. Can you, where we change the location of the wire to where. Okay. Anybody else? Yep. Good. So change the direction of the magnetic field. We don't want the magnetic field to act downwards, because we don't want the magnetic field will never be in the same direction as the magnetic force, right? It's always going to be perpendicular to that. But whatever way the magnetic field is pointing here, it's causing an upward magnetic force. If we want to keep the current in the same direction, if we simply reverse the magnetic field, whatever way it's pointing, make it point the other way, we're going to cause the magnetic force to point downwards instead. If we reverse the magnetic field and the current, what's going to happen? We change the direction of both of them. Magnetic field was pointing this way, now it's pointing this way. The current was going this way, now it's going this way. What's going to happen? We have no effect, right? We have no effect. Because by changing one of them, you reverse the direction of the force. By changing both of them, you reverse it back to the way that it was before. So it's going to remain hovering. All right? Take a look up at the board here right now. You don't need to copy this down. This is just like all of those other applications that we do. It's not a curriculum objective. It's not something that's going to appear on a test or an exam, at least not likely. Okay? If it does, you should be equipped to deal with it even without remembering the details of it. This is an electric motor, and an electric motor is one of the things that is present in. We talked about Oersted's discovery of electricity generating magnetism. Ultimately, that's going to lead to this design of the electric motor, which is present in all kinds of technological applications out there, from your hair dryer to your furnace to literally the vibration in your cell phone, the little electric motor that causes the vibration in the cell phone. We want to talk right now about how this works. We want to apply what we've learned over the last few days to see how the electric motor works. Whether it's in your hair dryer or whether it's in your cell phone, doesn't really matter. If you take a look at the bottom part of it here, we see a battery hooked up to a wire. You can see the negative side of the battery and the positive side of the battery. The current, of course, the electron current is going to go clockwise around through here, okay, leaving the negative end of the battery and go back to the positive end. But before it does that, it's going to take this kind of long roundabout path to get there. This electric current goes through this wire and goes through this conductor that we call a brush. This little black block thing there. It's a brush. And this brush is touching this thing that we call a commutator, which is also a conductor. It's touching it. It's not connected to it. It's not fastened to it, but it's touching this commutator. This commutator is connected to this wire that goes around here that we call the armature. Now what happens is that as the armature is in the position that it's in right now, the electric current goes clockwise around this circuit, goes through the brush, goes through the commutator, enters the armature, and goes around like this. Goes clockwise around through here. Goes back into the commutator on the other side, goes back through the brush on the other side, and then comes back out this way, back towards the battery. Does that make sense? All right. So what effect does that have? Well, we've now got an electric current going through a magnetic field. And when we have an electric current going through a magnetic field, we almost always get a force. That is, if the current is perpendicular to the field. It is here. Okay, you can see the magnetic field is going from north to south. It's kind of like this. And the electric current is going kind of like this. They're perpendicular. There's going to be a force on that wire. When you take a look at the paper that I have right now, this should reflect what you see up on the board, right? We got our electric current going clockwise through the system, and we've got our magnetic field going this way, from north to south, as in the diagram. Got it? If we have a magnetic field going this way, and an electric current, let's say at position A, at position A, electric current is going from A to B right here. Then we can stick our left thumb in the direction of the current, which is from A to B. Fingers in the direction of the magnetic field. Palm's going to point upwards, right? There's going to be a magnetic force upwards on this wire right here, A to B. Agree? Now, if we take a look at the other side of this electric motor, side C and D, there's going to be a magnetic force downwards because the current is going out of the page. In this case, we're going to stick our left thumb out of the page, fingers in the direction of the field, which is from north to south. Okay, that's from the left side to the right side. Palm's going to point downward. So there's a magnetic force upwards right here. There's a magnetic force downwards right here. What's that going to cause? What's going to happen as a result of that upward force on AB and the downward force on CD? It's going to cause AB to go up, and it's going to cause CD to go down. Make sense? So it's just turned, it's just spun 1/4 of a revolution. Why 1/4 of a revolution? Because when it makes 1/4 of a turn, this commutator right here is going to be in contact with the split, the insulator in the split ring commutator. So as it goes like this, contact is broken. There's now no electric current going through this. And because there's no electric current, there's no magnetic force. Make sense? So that's not a very good motor, right? You got an electric current going through the wire. It causes an electric force on both sides of the wire, one side up, one side down, to cause it to go 1/4 of a revolution. But if that's all it does, it's not going to dry your hair very quickly, and it's not going to heat your house very quickly, the fan on your furnace. So what happens at this point? Well, it keeps spinning a little bit because of inertia. Call it rotational inertia. Things that are spinning want to keep spinning, just like things that are moving want to keep moving. Okay? So it does. It keeps spinning a little bit. It's forced to make 1/4 of a turn, but it keeps going on its own because it's spinning. So it keeps going a little bit on its own. Notice what happens to the side AB and the side CD now. When it goes past the 1/4 of a turn, now AB is on the other side and CD is on the other side. You see that, guys? The sides are reversed. So let's say now it's going to look like this. My original AB is going to be over here, and my original CD is going to go over here because it's made not necessarily a complete 180 turn, but it's turned past the 90 degrees. So AB and CD have reversed. Now what's going to happen? Well, the electric current is going to start up again because the brush is now touching the commutator again. So as the electric current goes around here from still clockwise, but this time not ABCD, but rather DCBA, we're now going to have an upward force on side DC and a downward force on AB. So side DC goes up, right? Side AB goes down, and the exact same thing happens. Okay, it keeps spinning 90 degrees. Current is broken, no force. Keeps spinning a little bit because of rotational inertia. Now we're back to the way that we were before. AB on the left side. CD on the right side. Electric current still goes around clockwise, but now there's a force upwards on AB and a force downwards on CD. What's the net effect of this? Okay, if we repeat this cycle hundreds of times or even thousands of times, this. The armature spins. The armature would be connected to the fan on your hairdryer. It would be connected to the drill bit on your drill. Okay, it would be connected to the drivetrain on an electric car. It would be connected to whatever it is that you want to spin. So whatever it is that you want to spin will spin. Does that make sense? How could you get this electric motor spinning faster? We got it spinning. That's great. How do we get it going faster? You're driving your electric car. How do you make your electric car go faster? You've got your variable speed drill bit or drill, and you want to make it go faster because you're drilling through steel now as opposed to through wood. How do you make your hairdryer go faster at a faster rate? Okay, that's one way. You can have a stronger magnetic field by having stronger magnets. Good. What's another way? Increase the electric current. Good. So increase the magnetic field, increase the electric current. Most times, to be honest, when you're doing something where you're changing the speed of something kind of on the fly, like a drill, like a variable speed drill, Most times it's accomplished by changing the electric current, changing the resistance, and therefore changing the electric current, because it's easier to do on the fly. What's the other way then? There's one more way. Changing the magnetic field, changing the value of the electric current. What's the third way? You could increase the length of wire that's perpendicular to the field. How do we get all three of those? Some of you guys just may have been smart enough to think of them. But if we're not smart enough to think of them, we can always go back to an equation. Ultimately, what causes this thing to spin? A magnetic force. What's the equation that describes magnetic force? ILB. So if we increase the current, force increases and the speed increases. Increase the length of the wire, force increases, speed increases. Increase the magnetic field, force increases, magnetic field and speed increases. Good? I want to go back to what Sam said for a second. He said we want to increase, he was complete enough to say we want to increase the length of the wire that's exposed to the magnetic field and perpendicular to the magnetic field. Not just increase the length of the wire, but increase the length that's perpendicular to the magnetic field. How do we accomplish that? Usually what would happen is that we'd loop the wire around. So we've got this wire right here that's connected to the commutator, goes around here, goes around here, goes around here, and then it keeps going around here. We keep looping it around. Every time we loop it around, we double the length. Now, while length is important, this is wasted, right? Because this is all parallel to the magnetic field. But we got to have it there in order to have the circuit, in order to have the loops around on the left side and the right side. This is what's important. Okay, if we had 3 centimeters right here, and now we got 1, 2, 3, 4 loops, now we got 12 centimeters. Okay, this stuff, quadruple that as well, but it's useless because it's parallel to the magnetic field. Yep.
When it does like a quarter rotation,
yep.
would you argue that it's
Yes. That's a good question. He just asked, when it does a quarter of a turn, could you argue that it's now perpendicular to the magnetic field? And it is, because the magnetic field is going this way. The wire is pointing down this way now, right? So does it come into effect now? No, because when it makes 1/4 of a turn, it's the part of the commutator that the brush is touching is that insulator. So there's no electric current going through there. Right? So you got the wire perpendicular to the field, but there's no electric current going through the wire at that time. Does that make sense? Now, I wasn't going to talk about this, but I'll briefly address this since you asked that question. When it's in between parallel and perpendicular, it's at an angle, right? There is a force in that case, so it does become useful at that time, but not as useful as this part, A, B, C, D, because the A and the B and the C and the D are always perpendicular to the field, regardless of what the orientation is. Okay, and the maximum force occurs when it's perpendicular. The minimum occurs when it's parallel. And when it's something in between parallel and perpendicular, the force is something, but not perpendicular, but not max or min. That make sense? Is that good, guys? Are we going to have to recite what I just said? No. Are we going to see a motor on an exam? Probably not. But there's always a chance, right? Just because, it's an application just like any other application. What we want you to be able to do is kind of think about things and understand things. If you saw something like this on an exam, they'd give you some more detail than what you see on the board right now, but they probably wouldn't give you as much detail as I've just given you. They'd probably ask you some questions about what was going to happen, like I asked you questions as we were going through this. I got a couple multiple choice questions that I want you to work on. These are going to be pretty quick. Do them both together. 85 and 86, and then we'll take a look at them together once you're finished. Let's take a look at 85 here. It says a 50.0 centimeter length of wire with a weight of 0.389 newtons and a current of 0.250 amps. The wire remains suspended when placed perpendicularly across the magnetic field. What's the strength of the magnetic field? Look, what do we got here? We got a wire, not givens. Okay, we're not looking at givens right now. Okay, we're looking at bigger picture here. What do we know about this? What do we have? What's the situation? Okay. Way back to beginning of physics 30, right, with momentum. Okay, what's the situation, not what are the numbers we're given. We got a wire in a magnetic field, and it's perpendicular to the magnetic field. What do we know about that wire? What's going to happen to that wire as a result of that electric current going perpendicular to the magnetic field? What's going to happen to it? It's going to experience a force, right? It's going to experience a force that probably opposite to gravity here, because we know that the wire remains suspended. What do we know about the magnitudes of the magnetic force and the force of gravity? What do we know about how big those forces are, Adam? If it remains suspended, then we know the force of gravity and the magnetic force, they're the same. They've got to balance each other, right? We got a couple things that we got to draw attention to here. 50 centimeters, only one thing, I guess, 50 centimeters. That's our length of wire. What's this weight thing here? 0.389 newtons. If we say ILB is equal to M times G, what's the 0.389 newtons? Where do we plug that in? Yep. That's M times G. We don't even need to put the expression M times G in there because we know the force of gravity. We know the weight of it. So what are we looking for here? We're looking for the strength of the magnetic field. B is equal to 0.389 over the current, which is 0.250, times the length of the wire, which is 0.5. .11 Tesla. Agree? Good. And how would we express that? 3.11. Put the decimal place in there. Right? Notice that they're not asking for it in scientific notation or any exponent or anything like that, right? It's just the number. 86 is a wire that's 75 centimeters long and a current of 6 amps. The wire is at right angles to the magnetic field. Right away, we know when we read that this wire experiences a magnetic force. We want to know the magnitude of the magnetic field. I think this is pretty straightforward. We got a centimeters here that we got to draw attention to. We know there's a magnetic force. It's not suspended or anything like that, so we're just going to say F is equal to ILB. We're looking for B, so it becomes F over IL. Make sure you convert the 75 centimeters to 0.75 meters. What do you get from magnetic field strength there?
7.78.
This one does ask for scientific notation. Notice it's B times 10 to the negative W. We don't see that often. Okay, but how would we express that? As opposed to the ABCD, the way we usually see it, this would be expressed as 7.78. Don't forget the decimal place in there. Okay, we can't just put 778. Yeah.
So B, because I thought that B was referring to one digit.
Okay. You know what? That's a pretty common mistake, actually. B is not referring to one digit, and there's a couple ways that we can identify that. Okay, first of all, let me give you this. Three x is equal to 9. Solve for x, Joseph. Bad one. Oops. Let's say 9x is equal to 3. You're right. X was equal to 3 in that case. That's not what I wanted, though. I just wrote it down wrong. What's x equal to now? 1/3. Give it to me as a decimal number. 0.3333. You wouldn't say 0.3 for that, right? You might say 0.33. You might say 0.3333. I mean, in the end, it's repeating, right? Bottom line is, there's no issue with us saying x is more than one digit, right? We can say it's 2 digits or 3 digits or whatever, despite the fact that it's a single variable x. Well, if x can be more than one digit, why can't b be more than one digit, right? Make sense? The other way we look at that is to say, it says record your 3-digit answer in the numeric response section of the answer sheet, right? You always have to read what it says afterwards. Record your 3-digit answer or record your 1-digit answer. Probably won't ever be 1 digit. Occasionally it's 2-digit answer. It's great if it's a 2-digit answer because you got a 1 in 100 chance then, right? But if it's a 3-digit answer, make sure you put in 3 digits.